screen, and then we can start the presentation, please. And I would like to ask that if your group is presenting, then you have to put on your video so we can identify the various groups or the group members, or alternatively, we can do it this way. Whoever is presenting will put the video on. Then when it's time for questions, the rest of the members will all put their videos on. These are the two options available. Please note that every group will have a maximum of, I'm sure, let me check something. I'm sure if we give each group between 20 to maximum 25 minutes, we can have the presentation. Again, this is what is going to happen. Once a group is done with their presentation, we'll take note of all the questions. We'll take note of it. We'll allow the next group to also present. We do not want to pass comment such that or identify weaknesses that others will use to improve on their work, and that might affect them in terms of the scoring. So we will just take all the presentations that we have to do today. Then when we are done, we will open the floor for questions on each of the presentation that we had. So please take note of the modalities for today's presentation. Thank you. So David, is it group one that is starting?
Yes, please.
Okay, so can we have group one members sharing their screen?
Group leader Andrews, please, if you are online, you can share your screen. Or any of your members too can share the screen.
David, what's happening? Hello?
Yeah, Doc.
Yeah, what's happening? Where are the group one members?
Yeah, so I've communicated to their leader that they should share the screen.
Okay, if they are not ready, we can take group two so that we don't waste all the time, please.
Okay, sure.
Yeah.
So group two, if you are ready, please present your share your screen and then start with your presentation.
So is this group 2?
Yes, please.
Okay, group 2. Okay. So please, you can go ahead.
Since we can't hear you, if maybe you are talking, we can't hear you. Oh, wait.
Group 2, we can't hear. Is it group 2 or?
Yes, please. It's group 2.
We can't hear. Who is presenting?
Evios.
We can't hear anything, please. Or you are here to start? Hello?
Evios, please, can you hear us?
I think he has started, but maybe sound challenges.
Oh, then someone in the group should.
I think maybe he's unable to maybe sort out the sound this time or something.
Let's check whether.
Yeah, it is a sound. He said he's checking on it.
Oh, okay. That's
To show his face.
Yes, the reason why I want them to show their or to on their video is because they can ask someone to do the presentation on their behalf, which is not allowed. So they have to put on their video.
So, Evios, if maybe you are having challenge with your audio aspect, you can share your screen and one of your colleagues can start with the presentation.
Please, if you are not ready, can you stop sharing so that we take group 3? because we can't waste all the time like that, please, respectfully. If you can deal with your, yeah, so can we take group 3?
Group 3, maybe you are not ready. Let's move to group 4. Group 4, if your presentation is ready, please share the screen and then let's start presenting.
Hello, David.
Let's go.
Hey, what is happening? Can we have the next group?
Group 5, please, are you ready?
Group 4 or group 5?
So I earlier mentioned group 4, but no one responded.
Do
Group
you
4, please,
have
are you ready?
the,
Yeah, the group list.
yes. Can you share
Yes,
the group
please.
list with me?
Okay. I sent
I
you one
clearly
mail.
gave,
So let
you
me
send it to my
resend it.
email?
Yes, please.
Okay. If it's through email, I can just check. Group 5, is group 5 ready? Please note that if we mention and you don't present, please note that that ends it.
Hello, sir.
Yeah.
Please, can anybody do on behalf of the group?
Yes, that is it. Anybody at all in the group can present. Anybody at all in the group can present.
Please, hello, sir. Good morning. Please, can group 2 take it again because we were facing a little challenge.
Before the class, all these things should have been done before it's 8:24. So you should have done all these things before the time. Which group is this? Which
Group
group is this?
3. Group 3, sir. I don't know if my screen is showing.
Yeah, it's showing.
Okay.
What are you presenting on? What's your topic?
Yes, I'll be
Computer
presenting on
architecture memory
computer memory.
systems. Okay. All right. So can you mention your group members, let them respond, and then you start the presentation.
Okay, so this is group 3, and then we'll be presenting on computer memory. So I'll start by introducing my members. So we start with Mla Kumaho Elizabeth Akbene. Please, are you here?
Please, I'm here.
Sichofia Be. Please, are you here? Okay. Afo Benedict.
David, please take
I'm
note. When
here.
they mention the name and the person is not here, please take note of the person for me.
Afo Benedict.
All
Yeah,
right,
I'm
Doc.
here.
Okay. Christopher Henry.
Yes, I'm here.
Michael Odro Kwejo. Odai Ado Bismarck. Judith Na Ajele Doku.
I'm here.
Christian Atiemo Ado.
Present.
Echo Bansen.
I'm here.
Abubakari Suleiman
I'm here.
Lansa. Abubakari Suleiman Lansa. Roxin Kwesi Ampofo.
I'm here.
Nkua Caleb Acha. Inti Shadrach. Samuel Kusi
I'm
Mikkelsen.
here. I'm here.
Ernest Ejapon. Ernest Ejapon. Mensa Benjamin Atta, the presenter. I'm here too. And Ohene Evans.
Hello, please, Sechafi, I'm here. I was having network issues. I'm here. Sechafi, I'm here.
Yeah, Sacho, Mikel, I'm present. My name is not on the list. You guys couldn't add my name.
Is it
All
Samuel
right, we'll work
Kusi?
on that.
Samuel Kusi, I'm here. Samuel Kusi Michaels, I'm here.
Okay, all right.
Should I present?
Okay, you can go ahead. Go ahead.
Okay. Good morning, everyone. My name is Samuel. Today, Group 3, we are talking about memory system and understanding the core of digital data storage. Please go. Oh, why is my list on? Oh,
Should I move to the next slide?
yes, to the next slide. Okay. Introduction. Today, we are not just going to discuss about the definition of memory types. We are going to understand how memory directly impacts performance and experience. So, introduction is introduction to memory system. Primary memory, we have the RAM, we have the ROM, we have cache memory, we have virtual memory, we have storage memory, and also we do the comparison and the system flow. Then later we conclude. Please go to the next slide, please. Okay. Memory. You know, sir, every operation a computer performs depends on the memory. And the CPU is powerful. CPU is very, very powerful because whenever we talk about memory, we say CPU, CPU, CPU. But without fast and efficient memory, it becomes useless. So memory is the backbone of computer performance. It stores data and instruction for the CPU. And it's organized in a hierarchy based on speed, cost, and size. And now, because of modern IT, we have the trade-off of the speed versus the cost versus the capacity. Please move to the next slide, please.
Um, Presenter, please. I believe you are all learning. So when you are reading it, please take your time so that we can all get the understanding of it.
Okay.
So you can proceed.
All right. Thank you. Okay, here it talks about the memory hierarchy. We say from the top to the bottom. The top, say when I was doing research where I find out what a register cry is. If we say register, a register is a memory, but it's located inside the CPU. It's not like that normal memory that we see most of the time. So it is the fastest, but it's also the tiniest. It's very small. And we'll talk about the couch. After the registers, we move to the couch. The couch is also the second fastest. Then the RAM that most of us we have heard about RAM. It's also the second fastest. But the second storage devices, they are fast, but if you do the comparison of the memory, is the slowest. Because at first we used to have as uh, system units. You say system units have big hard drives, but now we are in the modern storage, so we have the SSD, we have the memories that are faster than that. Then we talk about the primary memory. We say primary memory is where the CPU works directly, and the RAM stores it get direct access to the CPU, and the RAM is also volatile. Volatile means uh when you are using your machine right now, the machine goes off. That's it. So it's a temporary storage. It depends only on active machine. But when when you are using let's say how we are presenting right now, if my machine goes off, I lose everything. The work become unsafe. That's what we mean by volatile. It stores things temporary. But when we talk about the ROM stores things permanently. So like when you boot up your machine, when the boot up starts the processing, it has already been processed. It stores everything permanently. That's why we talk about non-volatile. It's a direct storage. It don't Please, I'm coming. My machine is going off. Sorry. Okay, it stores things permanently. The RAM stores things permanently. And the RAM also, we have two types, we have types of RAM. The types of RAM, we have the DRAM and then we have the SRAM. Please move to the next storage, please. The next slide, please. Okay. We have types of RAM. We say that RAM is dynamic and is very essential. And we have the SRAM, we have the DRAM. The DRAM is very cheap and is slower. The SRAM is very fast and is very expensive because the DRAM it always needs refreshing. Every day it needs refreshing. That's why they say it's cheap and slower. But the SRAM, and you see couch memory instead of the main memory. So it's very fast. It depends on the couch. When I was saying, say the couch works directly with the CPU, so it's very fast. Please move to the next slide, please. We have limited time, so I cannot explain all plenty. So I'm briefing everything faster. We talk about the couch memory. It says that the couch is very fast. It's located close to the CPU and it stores frequent use data. We have the level 1, we have the level 2, and we have the level 3. You see, so when you open your normal browser, this is a clear the couch. Like how we open Google Chrome, Safari, what have you. When you open it, this is a clear the couch. As soon as you clear the couch, it becomes faster. So the couch is like, how should I describe this? It's very faster, but it's very slow. And it's not external storage that keeps everything permanently. That keeps a lot of things. So as soon as you clean it, it makes it work very, very fast. If the cache didn't exist, the performance of the memory would drop. That's what I'm saying. So if you don't clean your couch, the memory becomes very slow. It doesn't work fast. Your machine becomes very slow. Please move on to the next slide, please. the virtual memory. We say the virtual memory, when the RAM is full, the system doesn't just crash. It uses virtual memory. It's like extension. It's like extension of the RAM. But this one is much slower. It's not like it's much slower than the RAM. And they say it uses this as extra RAM. It extends memory capacity and uses paging technique. It's slower than the RAM. When your RAM is full, let's say your normal RAM you're using is full, you see, it can still store things, but it doesn't store it permanently. It's like extra for it. So when the time reaches, it go back to the RAM. When you clean the storage of the RAM, or you how should I say, delete some of the storage on the RAM, it goes back. So it stores things permanently for the virtual memory. Please move to the next slide, please. So here we talk about the second storage. The second storage, we all know what some of the second storage are. Let's say the SSD, the pen drive. It stores things permanently. You have your machine, but you have external storage there. So you just copy your things on it. Let's say your GCTU files. You just copy all your notes on your external memory. So wherever you do, you can get access to it. It also have a large capacity, but it is very, very slow. And it also, when your machine is off, you don't lose your things because the things on it are stored permanently. Please move on to the next slide. Okay, here we do the comparison. We say the comparison, we talk about the type, we talk about the speed, we talk about the cost, and we talk about the volatility, and we talk about the capacity. We say the couch is very fast. That's when we talk about the speed. When you talk about the cost, it's very costly. It's also volatile, which means things are stored on it temporarily, and it's very, very small. When you talk about the RAM, they say the speed is fast, the cost is high, it is also volatile, and the capacity is medium. That means the capacity on it, the storage on it is very small. It's bigger than the couch, but it's not that big. Then we talk about the secondary storage. They say the speed is very slow. But now we are having some SSD which the speed is fast, but if you talk about the hierarchy, it doesn't compare to the RAM and the couch. Also, the cost is very low and it's non-volatile because things are stored on it permanently. And now we have a lot of storage capacity, 2 terabyte, 1 terabyte. Now the capacity is always increasing. Please move on to the next slide, please. Here we talk about the real world insight. When we say it's a more RAM, that's better multitasking. We talk about couch improves speed. When you talk about uh we talk about couch, and when you're using so many systems, what's this word? Forgive me, I'll get back to that one. The SSD is faster than the HDD because now SSD now they are increasing. We have different types of SSD. Even the SSD itself, you have one which the speed are really faster than the other. So when your memory is low, the system start to slag. That's when we talk about the couch. Even the SSD, when you're using SSD and the memory is getting slow, the memory is getting full, your system start to lag. When you talk about the couch, I wanted to explain some part. Some part like big companies. These are big companies use big servers. So their couch, their speed is very, very different. Their speed, they are always cleaning their couch because they have servers that can store a lot of data on it. So when you talk about speed, their couch is the best. So you always make sure your couch, the space on it is very freely. Please, let's go to the next slide. So when we conclude, in conclusion, we say the memory hierarchy enables efficiency and different memory types serves a different role. The performance also depends on the memory design. That's how we are talking about the memory design. You said let me talk about SSD. Some SSD are some are designed to perform really, really fast than the other. So here is how we bring any conclusion to our presentation. Please, do you have any question?
So we move on to
okay.
the next group. You need to jot all your questions down after the presentation, then we can ask questions.
Okay. Thank you
So
very
as a
much.
group is being presenting, be jotting your questions down. So after the presentation, then we can go ahead with our questions.
Okay.
Can I stop sharing?
So yes, please.
All right, sure. Thank you.
So
Group 2 would like to take over.
group 2.
Okay.
We have only 20 minutes to present. So from now going, I'll be timing each group. So when it's your turn, you come early. When I mention your name, I mention the group name. You come and then you present your work. And then if the time is due, you just sign out and then the friends will take over.
Okay.
So as it was earlier said by our lecturer, Dr. Patrick, each group members are supposed to show their video, the one presenting and also the members. Thank you.
Good morning, group. So this is Kudjo from group 2. We were having Elvis to present, but he's taking his time. But we will mention the group's name. For Tete, if you're here, you will say you're present, then we will move on. Kudjo ain't not been. Okay. Kudjo ain't not been the one speaking at the moment. Angelina, appear someone.
I'm present.
Okay. Luke Awache.
Present.
Justice Odro. Justice Odro. Daniel Delacosi.
Present.
Collins Nana Kweku Edufo. Collins. Hayford. Yao. Bismarck. No. Please, can we move to the next slide?
Which group is this, please?
Please, dog group 2.
Okay. And what are you presenting on?
We are presenting on CPU. Look.
CPU.
Yes, doc. So
Who gave you the topic on CPU?
the central processing unit, we said we are supposed to pick any one of the units to present on.
Okay. All right. You go ahead.
Okay. So please, can you move to the next group so that I can mention the names of those who are around? Yedu Osman Mohammed. Philip. Daniel. Robert Oku. Rukaya. Ebenezer Chumesi. Elvis Elikem.
Present.
Then please, Elvis, kindly take over. Priscilla Mausi.
Present.
Emmanuel Dako. Boss Francis.
Present.
Theophilus Amo.
Present.
Richard Flo.
Present.
Okay, so please can you move to the next slide? And kindly note, Elvis, if you're around, please let us know and take over, please, as a presenter. Okay, so let's continue. So we have our outline, which is introduction to CPU. And we said, what is CPU? Meaning CPU is the central processing unit, or we can say the CPU is the brain of the computer. And when it comes to the CPU, it has many other functions that it performs. One of it is the arithmetic unit, and which controls the calculations and the logic behind what the CPU does. And we have the control units and registers, which also performs the directed traffic and fast storage to help process of data to be executed. And we have the instruction execution cycle, whereby it goes through a certain process for the data to be processed. We have one to be fetched, decode, execute, and store. Please move to the next slide. The central processing unit. So with the central processing unit, as we have there is the electronic circuit within a computer that executes instructions to make program work. It often refers to as the brain of a computer. So with the central processing unit, we can say that it is the core part of a computer, which being a mobile phone or a personal computer. It helps in with the operations and fast processing of information, and it also serves as a background through the hardware aspect and also to help present or process information to the software aspect. So please, let's move to the next slide. So the basic function of the CPU, we have the control unit shown on the diagram over here. So on the top side, we have the control unit, and we have within the CPU as a control unit, we also have the arithmetic logic unit within it, performing the logic operations on it. So when we go to the left side of it, we have the input of information. And when the input is being input by a user or from a user's end to the system, is where the CPU process all the logic aspects, executes it, fetch for all details, then brings out the output. And we have the down aspect as the memory. So the memory where we have the registers and the staffs to also process those information by fetching, coding, and also bringing out the exact information needed to be output. So it is the primary function. So its primary function is to fetch, decode, execute, and store, are the same as write back. Instructions received from the software, like a word processor or web browser, and to control the flow of data between other components like memory and storage. Please, let's move to the next slide. So as the CPU, we have a core component of the CPU. And with these core components of the CPU, they stand to perform the most work in which the CPU stand to do. So while complex, the CPU is architecturally composed of three main parts. We have the arithmetic logic unit, the ALU. That one handles mathematical calculations for the processing of information. Then we come to the control unit, which direct the operation of the processor. Then we come to the registers, ultra fast storage location inside the CPU. So please, let's move to the next slide. So when we come to the arithmetic logic unit, its role as it does is to handle all mathematical calculations and logic operations. So with that mathematical with the mathematical calculations and the operations, we have the arithmetic, the addition, the subtraction, multiplication, and the division. And when it
Hello,
comes to the
Paul.
logic,
Hello, Paul.
as Doc, Kudjo is the
Okay.
one talking and Paul is the one presenting.
Okay. I've just been alerted that we have to ask questions right after the presentation, but my final comment will be later. So just get ready. After your presentation, the first two groups that are presented will ask you questions before we'll continue with the next one.
Okay, Doc. Thank you, Doc. Okay, so as we are moving on, we said that the arithmetic logic unit handles mathematical calculations and logical comparisons. So with the operations, we know some of the operations to be addition, subtraction, multiplications, and division. And when it comes to the logic aspect, where we have the comparing values as the Boolean logic, the and, or, nor, the x, nor, or the X gates, which helps in the execution of which help in the execution of logic processing. When it comes to the NOR, the X nor, we know that when it comes to the electronic aspects, it sends signals to be as on and off to help us indicate how the hardware also transmits information logically in that aspect. So please let's move to the next slide. So we have the control units. We showed within the diagram for the CPU where we had the control unit and where we had in the previous slides where we had the output input over there. So when it comes to the control unit, this aspect of what it does in the CPU is that it directs and coordinates all activities within the CPU. Mostly the key tasks where it's controlling it does is that one, it decodes instructions whereby information has been transmitted from the input side to the CPU. So it goes instruction, translate them into actions, and also generates control signals to tell the other components, the ALU, what to do. So we have a simple diagram on the left side, which of the instruction registers straight into the control unit. And within the control unit, we have control signals internal to the CPU. Then we have control signals, external system bus. Then we also have control signals from the external system bus. So that is the aspect of what functions the control unit does. Please let's move to the next slide. So we come to the registers. So the registers are a tiny ultra-fast storage location inside the CPU for storing data temporarily. So what it does is that you see with the key type of registers that we have is the program counters hold the address of the next instruction. So we can have like a printer where we have instruction set. So within these instructions, we have multiples of instructions set. So we have a place where it holds all these instructions and takes time to execute them step by step. So that's what the program counter have. And we have the instruction registers, the R, holds the current instruction being executed. So with the IR of holding the current instruction being executed, let's say we have the registers saying we said the registers for storing data temporarily. So with the IR holds the current instructions, that means with the moment an instruction is being executed, whereby the program counters holds the instructions, the multiples of instructions being executed, the instruction registers execute them step by step in order for the information to go as in according order. Then we come to the calculators, store the results of calculations from the ALU. Please, can we move to the next slide?
Hello.
Hello.
No, Robert.
Oh, okay.
Okay.
Okay, so let's continue. So we have the memory address registers and we have the memory data registers. So with the memory address registers, hold the address of the data in memory to access. And with the memory data register holds the actual data being transferred to or from the memory. So what is that what it does that the memory address registers we can say we can make take it as maybe like a community where we have the layout of the community. So we have the intersections of that layers. So that aspect holds the units of the housing of these communities. And where the memory data register does is that it holds the actual communities that are within the areas. So we say that the memory address register holds the address of the data in the memory to access. So it holds every single point of the location of the houses. Where we can say that with the memory data registers holds the actual data being transferred from the memory. So it holds the entire data, which is, let's say, if it is within a multiple communities, it holds that numerous various multiple communities. But with the memory address registers, it holds the single unit in housing within the communities. Please let's move to the next slide. So we have the instruction execution cycle. So with the instruction execution cycle, we talk about the memory address by the registers. So with this side, this is how the instruction is being executed or the process that it goes through before it is being output. So the cycle of the steps the CPU perform to execute a single program instruction. The CPU operates by continuously repeating the cycle. This is often called the fetch, decode, execute, store cycle, or a machine cycle. Please let's move to the next slide. So with the instruction execution cycle, at the fetch stage, what it does is that the CPU at the fetch stage, what the instruction does is that the CPU retrieves an instructions from memory by the address bus, pinpointing the required location in RAM of the instruction. So with the previous example that I made about using the community as an example, as a community as a whole large, and the housing unit within the community. So this time, the first stage would pinpoint the required location in the RAM of the instruction. So we would locate the exact stage, the exact program in which it was being executed. So we gave an example of multiple communities and within the housing. So let's say it comes from even the first instruction being executed. The first stage will relocate which which instruction, exact instruction in which the information needs to be retrieved from. Then we come to the decode stage. With the decode stage, the CPU interprets the fetched instruction. It identifies the operation into bracket mathematically or logically to be performed and determine the operation involved. So right now we've located where the information is coming from by the first stage. Now the decoding stage is where we tell the exact instruction that it is. It is a mathematical, or is it an arithmetic instruction, maybe performing a basic math instruction or performing a higher instruction. So the decode stage differentiates what type of instruction that it is required from us to, or required from the CPU to perform. Let's move to the next stage, please. The next slide. So as we've moved from the fetch stage to the decode stage, now we come to the execute stage where the CPU carries out the execution of the instruction. That is carrying out the necessary operation specified by the instruction during the decode stage. So we talked of the decode stage specifying the aspect of which instruction it is when the information is being fetched. So if the information is a basic math calculations, the decode stage will differentiate for us. Now, as the decode stage have done that, this is where the execution stage comes in. So it carry out the necessary operation. So right now, we need the exact solutions in order, or the exact, like let's say use tools, exact tools, or the exact necessity for the arithmetic or the logic reasoning to perform. So the execution stage give us the necessity in helping the necessary operations specified there to be executed during the decode stage. Let's talk about the write back or store stage. So that one, the results of the executing instruction are stored back in the memory or the designated registers for the output. So it go back to the memory or the registers there in order for referencing. So if right now we've performed these tasks, now it goes back for referencing sake. Please, let's move to the next slide. Okay, so that would be that for the CPU. Thank you.
Okay, thank you. So based on my earlier submission, as I stated, someone said they are likely to forget some of the things, so they want to ask the questions right after the presentation. I'll
Okay,
open the
doctor.
floor. If you have any question, please go ahead and ask before we continue. Please, any question from any of you? Hello?
Yes, so I have a question for
Yeah,
for
please go ahead and ask.
yeah. So my name is Christian. I want to find out from the
Kudjo,
gentleman
Kudjo.
who presented,
It's
and
Kudjo.
that yeah. So does the ALU, that's the arithmetic logic unit,
Logic in.
only deals with arithmetic functions? Does it only deal with arithmetic functions? Because you did mention of this mathematical functions, and if it only deals with arithmetic functions. Thank you.
Okay, so
Hello.
Christian. Yeah. Hello, Christian, can you hear me?
Yes, I can.
Yeah. So Christian, in the slide, we didn't talk only of the arithmetic unit, but I made mostly what I talked about was the arithmetic unit, but it doesn't only do that. If we talk about the logic reasoning aspects as well, where we have the NOR, the XNOR, or the OR aspect too. So with the logic reasoning aspect, whereby with the arithmetic aspect, you see with the basic calculations and stuff, it does, but not only that. So with the logic reasoning aspect too, maybe when you are processing an information whereby you need higher advanced you process about an information. So the logic reasoning, we talk of the aspect where you use logic and or XNOR. We did that some of these in I think one of the courses. So with this one, maybe you are transmitting the information on the hardware aspect. I get in it. So in the arithmetic aspect, we use an example of the Word processor, Microsoft Word, whereby maybe you are drafting information from the input aspect. So that's on the software aspect. When it comes on the hardware aspect, the transmitting of the information, I get in it, to the software aspect to the LU2 does that, or the CPU2 does that. So that's why I said about something using the electrical aspect. Maybe we have the open or close gate. So through that, these ones also send signals in order for the hardware aspect to communicate with the software aspect. So the CPU or the LU doesn't do only that, but it does more to it. Christian, please, is that okay for you, or you need more clarification on the subject matter.
Hello, Christian.
Yeah, so as
Yes.
he stated,
Yes. So I think yes. Please can you hear me?
Yes,
Okay.
we
yes, we
can
can
hear
hear
you.
you.
Yeah. So I think you've mentioned the arithmetic operations. That's the addition, subtraction, multiplication, and addition. You spoke about the logical operations as well. That's the and, or, not, and the XOR.
The X no.
Okay. And I
Yeah.
think you left one. The XOR, yes. So I think you left one, that is the bitwise operations. I think there is one that you left, the bitwise operations, that's the shift and the rotates. So the
Okay.
arithmetic logic also does that.
Okay, sure. Thank you for that.
Thank you.
Okay. Any other question? Now, I want to ask the group, can you help us by distinguishing or providing a distinction between the control unit and the instruction set?
Okay, so Doc,
Yeah.
I will let Elvis said you want to talk on that one. So I'll let Elvis talk on that.
Okay.
Hello, Doc.
Yes,
So
please.
with
Go
the
ahead. Yeah.
control unit, it is
Yeah.
a component inside the CPU that directs the other components in the computer system what to do, the specific tasks to do, and at what
Okay.
time to do it using
Okay.
the clock signal. And then
Okay.
the instruction set architecture
Yeah.
is a series of instructions that is embedded into the CPU. So during the construction of the CPU, the instructions set is put into the CPU so that the CPU would know the type of how to execute certain types of instructions. Hello, sir.
Yeah, I'm here. I'm listening.
Yes, sir. So the please with the instruction set architect, please, are you talking about the fetch, decode, execute cycle?
You finish your explanation and then I can come in.
Okay, so like I was saying, I know the control unit controls the signals in the computer system. So whatever signal that comes into the computer system, the control unit tells the right component in the computer system what tasks to do and at the specific point to perform that particular task.
Okay. Does the control unit fetches instructions from memory?
No, sir. So the control unit sends control signals to the address bus to fetch the instruction from the memory using the specific instruction address.
So are you saying that the control unit does not fetch and does not decode instructions?
So the control unit alone doesn't fetch instruction. So the control unit
Okay.
works hand in hand with the address bus, the memory address register, and other registers to access the instruction from memory.
Okay.
Yes, sir. So what I'm trying to say, the control unit alone doesn't fetch the instruction.
Okay, but it does.
Yes.
Please.
So
yeah.
Okay, so when the CPU, the computer system receives the signal of the instruction, the program counter sends the address on the address bus. Then the address is being sent to the memory address register. Then the instruction is located inside the memory using the memory address register. So the control unit sends the control signals for all of these processes to be done. So the control unit work hand in hand with the program counter and memory address registers to fetch the instruction to be decoded.
Hello,
Okay,
Doc.
thank you. Yes, please. Yeah.
Sir, this is the boss. I'm also in group
Okay.
2. I wanted to come in.
Okay.
The control unit is more like a conductor. It does not only fetch instructions, but it also manages the entire life cycle through the instruction cycle.
Yeah. Hello?
Hello?
Are you done?
Yes, sir.
Okay. I agree with you on that. Colleagues, any other question? Okay, if there's none, let's pick the next group, please. Let's pick the next group.
So group 5.
Group 5 here, please. Good morning.
Yeah, good morning.
Good morning.
So before he starts, please, group members, when your group is presenting, please kindly show on your camera and show your video so that we know those who are present at the moment. You can go ahead. You have 20 minutes to do your presentation.
Okay. Good morning, everyone. My name is Tahir Abdul Shakur, and on behalf of Group 5, I will be walking through our presentation on memory systems in computer architecture. Let me begin by acknowledging our team members listed here, led by Mr. Ebenezer, with Mr. Abraham, our assistant lead. And we've worked collaboratively to bring this presentation together. Hello, can you hear me, please? Hello.
We can hear you.
Yes,
we
can
hear
hear
you.
you.
Okay. Here is what we'll be covering today.
Please kindly
Hello.
mention your group members' name so that we know those who are current present.
Okay. 1, Dahir Abdul Shakur, I am present. I am the one presenting. And 2, Ababio Ernest. I don't know if he is present. Okay. Ado Donald. Donald. Okay.
We move on to the next person.
Okay, Godfred. Okay. Okay, Amon Kwaibo. Theodore. Albert. Okay. Gabriel.
Present.
Okay. Dorcas. Sir, we are all present. We are all present here, please. May I proceed?
Please go ahead and present.
Okay, thank you. Here's what we'll be covering today. We'll start with an introduction to memory systems, then dive into the various types of memory. Primary memory, which include the RAM and ROM, cache memory, virtual memory, and secondary storage. Then we conclude by examining how all these components fit together in what we call the memory hierarchy. So what exactly is memory in the context of computing? At its most basic level, memory is a process by which information is encoded, stored, and retrieved. Memory systems are essential components of every computer system. They are in fact the backbone that enables every operation on our computers. Every time we open an application, edit a document, or even move our mouse cursor, the memory systems are at work. The central processing unit depends on memory to retrieve instructions and process information. The CPU, the brain of the computer, depends entirely on the memory to function. It constantly fetches instructions and data from the memory to execute tasks. Without the memory, the computer, the CPU, would have nothing to process. Now, the memory in computer systems are generally organized in different categories that work together to improve speed, efficiency, and storage capacity. These categories include the primary memory, cache memory, the virtual memory, and secondary storage. Together, they form a cohesive system that balances speed, capacity, and efficiency. Let's start with the primary memory. Primary memory is the main memory it's the main memory directly accessed by the CPU. When, let's say, when you're actively working on your computer and say typing a document or browsing the web, the data resides in the primary memory. It stores data and instructions currently being processed by the computer, and it is characterized by high speed, limited storage capacity, direct communication with the processor. For high speed, it is designed to keep up with the processor, which operates at numerous cycles per second, probably billions of it. For limited storage capacity compared to the hard drives or SSD, the primary storage is relatively very small. And in our modern computers, we can have as far much so as it ranges between 4 gig to 6 gig. These memory types work together to ensure the computer operates properly during processing and system startup. Next, we'll be looking into the random access memory. The random access memory is a temporary storage location used by a computer to hold data and programs currently in use. The key characteristics of RAM include: one, it is volatile, meaning its contents are lost when the computer is turned off. Two, it allows fast access to data. Three, it supports the execution of multiple programs simultaneously. Four, it allows data to be both read and written. And lastly, it stores information only while tasks are running, meaning it is temporary. And here's an example of a RAM. It includes the DRAM and SRAM. But the DRAM is majorly the DRAM is the most common type, which it's an example of the RAM. It runs applications such as web browsers, Microsoft Word, or PowerPoint. It has temporary storage of files being edited. It also supports multitasking operations. It is important to note that the greater the RAM capacity, the more efficiently a computer can perform multiple tasks. Next is the ROM, the read-only memory. The ROM is a type of permanent memory that stores essential instructions required to start a computer system. Its key characteristics include: one, it is non-volatile, meaning data remains stored even when the power is turned off. So it contains instructions used during the booting system. Three, it cannot easily be modified by users. While some ROM can be updated in normal operation, users don't write to ROM. It's why it's read only for a reason. Without the ROM computer, you wouldn't know how to communicate. Your computer wouldn't know how to communicate to keyboard, display, or hard drive during startup. Next, we'll be talking about the cache memory. The cache memory is a small, high-speed memory located very close to the CPU. It is small, ultra-fast memory located physically very close to the CPU. It is actually built in modern computers, actually built in the CPU chip itself. Its sole purpose is to store frequently used instructions and data to the processor so that the processor can access them almost instantly. The characteristics of cache memory include: one, they are very fast. They are extremely fast. They operate at the processor speed. Two, they have smaller storage capacity compared to RAM. They are typically measured in megabytes. Three, higher costs per unit of storage. The cost to make a unit storage of the cache memory is very much expensive, and that is why we don't just make all memory this fast. Cache memory improves system performance by reducing the time required for the CPU to access data from main memory. This helps the overall processing efficiency. Next, we'll be talking about the virtual memory. The virtual memory is a memory management process that extends the capacity of the main memory. It allows a computer to use part of the secondary storage as additional memory. How the operation of this is when your RAM becomes full, the operating system identifies data that isn't actively being used and temporarily moves it to the secondary storage, that is your hard drive or SSD. This process is called paging or swapping. When the data is needed again, the system swaps it back into the RAM, potentially moving all the data out to make space. From the user's perspective, you can continue working even though you've technically exceeded your physical memory capacity. The advantage of the virtual RAM include one, to run a large application that won't typically fit entirely in the RAM. So its support for multitasking. You can keep many applications open simultaneously, and lastly, improve memory management across all running processes. However, it is slower than the RAM because it depends on storage, on secondary storage devices. The secondary storage device operates at milliseconds. Well, that's why when your computer starts using virtual memory heavily, you might notice performance slowdowns. Next is the secondary storage. Secondary storage refers to devices used for long-term storage of data and programs. Unlike primary memory, secondary storage retains information even when the computer is powered off. Common examples include the HDD, hard disk drives, the SSD, solid state drives, flash drives, memory cards, CDs, and DVDs. The characteristics of secondary storage include large storage capacity, slower access speed compared to primary memory, permanent data storage, uh, secondary storage is essential for storing operating systems, software application, documents, and multimedia files. Now, let's bring everything together by looking at the memory hierarchy. This is fundamental concepts in computer architecture that explains how different types of memory are organized based on three factors: speed, costs, and capacity. At the top of the hierarchy, closest to the CPU, we have the CPU registers, the fastest memory of all, but extremely small, typically just a few hundred bytes. Next comes the cache memory, still very fast, but larger than registers. Then the primary memory, they are slower than cache, but significantly larger in capacity. At the bottom is the secondary storage. It's the slowest, but with greater capacity and the lowest cost per unit of storage. There's an inverse relationship at play. As you move down the hierarchy, the speed decreases, but the capacity and cost of efficiency increases. Moving up the hierarchy, the speed increases, but the capacity shrinks. To wrap up, let's reflect on what we've explored today. The memory systems are fundamental to computer operation. Without them, the CPU would have nothing to process and no way to store results. Each type of memory plays a specific role. The primary memory handles active data and system startup. The cache memory accelerates processing, and the virtual memory extends the memory capacity, while the secondary storage provides permanent long-term storage. Together, these memory components form an integrated system that ensures efficient processing, storage, and retrieval of information. Understanding how they work together helps us appreciate not just how computers operate, but also why certain design decisions like adding more RAM or upgrading to an SSD have such significant impact on performance. Our primary reference for this presentation was the course material from Doctor's lectures, specifically Unit 6. I'd like to thank all the group members for their contributions and thank you all for your attention. Thank you. And that's it.
So class, any question?
Yeah, so I have a question. I will humbly request that the group provide some key distinction between the primary and the secondary memory.
So I hope you heard the question.
Oh yes, I will. Sorry about that, please. The primary memory is the main memory, which includes the RAM and the ROM, while the secondary memory is storage devices like the HDD, SSD, flash drives. Into the computer access, the hold on.
Okay, so can I come in? My name is Ernest. Ernest
Oh,
Abebio.
okay.
So when we talk of primary memory, they are volatile, which means when the power is turned off, all the data the memory has stored just erased. And when you talk of secondary memory, they are non-volatile, which means when the computer is being off, the data is kept permanently. Thank you.
Okay, so my name is Mustafa Razak, and I also want to contribute in addition to what my brother presented earlier on. So with primary and then secondary memory, when we talk about usage, the primary is for immediate usage, and then and it's active, and then the secondary is for long-term storage. And then with the two, when we compare speed, with the primary is faster, but loses data when the computer is being turned off. But with the secondary is slower and then retains data when being turned off.
Okay. In terms of speed, can you talk which of them is faster?
Okay, so in terms of speed, primary is faster.
All right, thank you. Can we have, you spoke about the cache memory as well. Can you explain the cache memory and the various types?
Okay, sir. So with a cache memory, is also extremely fast, but very very small in nature, and then it's expensive too as well, and also it is volatile. So the example of cache memories, we'll say um, the RAM, that is the random access memory. And then with the cache 2, we have three levels of cache memory. Then the level 1 is the fastest and smallest, but directly into the process core. And then with the second level of cache memory, it is slightly slower, often on the processor chip. And with the last one, it is the largest and slowest, usually shared among all processing um, devices. Thank you, sir.
Class, any other question?
Hello, sir.
Yeah, please go
Yeah.
ahead.
So please, I wanted to know the difference between the DRAM and then the SRAM.
Uh, the group members, please, there's a question. He wants to know the distinction between the D, that is the dynamic and static RAM.
So, my name is Ibrahim Mejida. With the dynamic RAM is slower and usually used for the it's usually used by the main memory. But the SRAM is faster and used for cache memory and those stuff. Thank you, sir.
Can you give us in terms of capacity, talk about capacity?
Hello, sir. So in terms of the capacity, the DRAM is higher dense than the SRAM.
Okay, thank you. Any other question?
Yeah, sir. I want to know the primary difference between the BIOS and the ROM, which you've mentioned in your presentation.
Please, can you come again with your question? I'm not sure. We get the question right.
I'm saying that I want to know the primary difference between the BIOS and the ROM. As you were presenting, you in under the ROM, you mentioned something BIOS, and so I want to know the primary difference between the two. You get a question now?
Yes, yes.
If I get your question, BIOS is just it's a program. When you talk of ROM, is memory chip that stores
the program which is being done on the BIOS. I don't know if that answers your question.
Sir, please, to add on what my colleague has mentioned, the ROM is the hardware, while the BIOS is the software. The ROM is like a physical chip that holds the data permanently, while the BIOS is the actual program stored on that ROM chip.
Yes,
Okay,
and
so
then
this
to add
one,
up to what my colleagues have said. So when you dismantle a personal computer, you'll be able to see the ROM in it. But with the BIOS, it's like a software that operates in the PC. But that is not visible, or that you will not be able to see physically. It runs in the system, but you are not able to see it or feel it.
all right, well noted. Okay.
Hello.
Hello, sir.
Hello, sir.
Yeah.
Hi.
Yeah. Can we take the next group?
Group 6. Group 6, please, can you share your screen?
I think the other one hasn't on share, so you should on share.
Hello? Hello?
Hello. We can hear you.
Good morning.
Good
Morning.
morning.
Yeah. My name is Delato Agbenyu. I'm presenting for Group 6. So I'm coming on. I want to send a group list.
Please, let's note this information. As a group is being presented, the next group should start preparing so that when we mention your name, you just go straight sharing your screen.
Now then I can use my screen. Oh, who
Yes,
is
your
sharing?
screen is visible. Please, who is presenting?
Ella, the screen is on.
Yeah.
Please
Um,
and share your screen so that I'll do it. I'll do it over here. And share the screen.
all right.
Time is going. At least from group 1 to by now, everybody should be ready.
Okay, so we are presenting on performance metric and evaluation. Here is our group members. We have Mopopo Escobar. And please, should I continue with the names?
Yes, please.
Okay, so we have Innocent Delano Nutako,
Present.
Daglo Isaac Mauli, Samuel
Present.
Ampofo, Solomon
I am
Tato,
here.
Present.
J. Ernestina, Dennis Kwete,
Present.
Theophilus Mauli, Delato Agbenyo, that is me, Bright Delali,
Present.
Richmond Abochi, Justice Youngson, Kobe Sakite,
Present.
Elvis Ajay, Amponsa Prisla, Pascal Cunha, Maxwell Mensah, Bernard Osei,
Present.
Udu Isham, Samiatu Abu,
Present.
Kingsley Boatin, and Ernest Ajapon. Okay, so I'll go straight to the presentation. As said earlier, we are presenting on performance and then.
Hello.
Hello.
Hello, please. Your Hello. screen is too small. We can't see it well. Yeah, I didn't hear my name, sir.
No, Kelly
I
is
didn't hear my name.
sharing his screen from his phone, not his laptop. So.
Please, your
Well,
name.
well. So don't
Your
you
name.
have any group member that has a laptop?
Hello.
Hello, your name. Your name.
Yeah, I mean, if
Hello. Wait, check.
Roger,
Yes.
yeah, I mean, if it's okay with you, can we share so that you can do the presentation? If it's fine with you.
Please come again.
I'm saying that if it's okay
Kelly.
with you, let me share it from
Kelly
here
Enoch.
and then you do the presentation, okay?
Okay.
All right.
Hello. Wait. Kelly Enoch. Avu.
Hello.
All right, you can share it from your laptop.
Hello.
Hello.
Yeah, we are group 4 and we are ready. So whilst we wait for him, can I also step in?
Group 6 is presenting right now.
Please. Who's
Okay.
you want to share it from his laptop? Okay, so first of all, please, we are sorry for the inconveniences. Now we are settled to continue. So we are presenting on performance metric and evaluation. So we want to talk about clock speed and CPI. We are saying clock speed refers to how fast a computer or a CPU executes instructions. How fast the CPU executes instructions. It is mostly measured in hertz, popularly known as gigahertz. So we are saying a higher clock speed means more cycles per second. Higher clock speed means more cycles per second. That is 3 gigahertz processor. A 3 gigahertz processor is equal to 3 billion cycles per second. So CPI are cycles per instruction. It is the average number of clock cycles required to execute one instruction. The average number of clock cycles required to execute one instruction. It measures how efficiently a processor executes instructions. And then we have the formula for cycles per instruction, CPI. Is equal to total CPU cycles per instruction count. Total CPU cycles per instruction count. So let's look at the relationship between the clock speed and the CPI and then the number of instructions. So we are saying performance depends on clock speed, the CPI, and then the number of instructions. So the CPU performance mostly depends on these three things. So we have the execution time formula, which is CPU time is equal to instruction count times CPI clock speed, CPU. And then we have the CPU time is equal to clock speed, instruction count times CPI. Lower clock speed per instruction and higher clock speed is equal to better performance. A lower clock speed per instruction and then higher clock speed is equal to better performance. So yeah. Then we also have million instructions per second, million instructions per second, and then floating point instructions per second. So millions instructions per second measures how many millions of instructions a CPU can execute an instruction per second. Then the floating point operations per second measures performance for floating point calculations. So floating points are mostly decimal numbers. So the floating point per second, floating point operation per second is mostly used in scientific computing. And then we have various examples of floating point operations per second. We have the million floating point operation per second. We have the billion and then the trillion. So as said earlier, we use those calculations in scientific simulations AI and machine learning, and then graphics processing. Performance measurement techniques. The first technique is benchmarking. Benchmarking, which is running standard programs to evaluate system performance. And then we have different types of benchmarking. We have the synthetic benchmark. Example is test programs or running tests against a program. And then real world benchmarks, that is the actual applications. When the application is actually running, then maybe, or when users are using the applications, then we can also benchmark using the available data. Then we also have another technique is execution time. The most reliable performance metric measures how long a program takes to run. How long a program takes to run. Different types are the CPU time. The CPU time. And then we have elapsed time. That one includes input, output, operations, and then the waiting time. Then another example, another type is a throughput or throughput. The throughput, the number of tasks completed per unit time. The number of tasks completed per unit time. Important in synthetic systems handling multiple users. And then we also have latency. Time taken to complete a single task. A single task. It is important for real-time systems. And then another technique is profiling. Profiling is analyzing which parts of a program consumes the most time. Which part of a program consumes the most times. It helps to optimize performance. And then we have the last one is Amdahl's law. It's used to find the maximum improvement possible by enhancing a part of the system. So we have some key ideas. Improving one part of a system has a limited overall effect. Improving one part of a system has a limited overall effect. And to summarize, we have clock speed and CPI determines how fast instructions are executed. And then millions instructions per second and floating point operations per second measures performance but have limitations. Then we have performance evaluation relies on execution time, benchmarks, throughput, and latency. Okay, thank you. So this is the end of our presentation.
What is your topic again?
Performance metrics and evaluation.
Trust me, you have not done any presentation. Consider it that you've not done any presentation. Because if I want to grade or score you, I'm not going to give you anything more than 10. This is not a presentation. So you go back, work on it. We'll give you another opportunity to come and present.
Okay.
Hello, sir. Hello, sir.
Yeah.
Please, we want to know why it is not considered a presentation.
I'll talk about it later.
Thank you.
Hello, sir. Hello, sir. Group 4 is ready, please.
Hello?
Yes, sir. Group 4 is ready. Can I share my screen, please?
Group 4.
Yes, sir.
What are you presenting on? You have to do it fast. I have another class, so you have to do it fast.
All right, sir. We are presenting on.
So group 4 will be the last group for today. Group 4 will be the last one, and then we'll continue next week.
Yeah, so it's group 6 who just presented, so they will be the last group.
All right. I'm sharing my screen in a moment. Please, my screen visible.
Yeah, it's visible.
All right. My name is Godola Bushwansa, and I am making the presentation on behalf of my colleagues from Group 4. So I'll start by mentioning the names of my group members. Emmanuel Baja, Edward Baidu,
Yes, I'm here.
Samuel Usuansa,
Present.
Manu Matilda,
Present,
Penny,
please.
Evelyn Penny,
Yes, sir.
Latte Kafui Maswell,
I'm here, brother.
Jantua Edwin Edem, and myself, Owusu and Sangola Love and Koma. Samuel Ej Tete, Lambert Yao,
Present.
Abouku
Present,
Lambert
Lambert.
Yao,
Lambert, I'm present.
Rafik Adam Kudjo,
Present.
Eunice Frimpong, Ata Aaron Moses,
Present.
Alex Kaba Audi, Alex Kaba Audi, Joshua Gidiglo, Vida Kos Utojo,
Present.
Maxwell Usuapia,
Hello, please, I'm present to Ransom Frempong. I'm present. Sorry.
okay, Frimpong Richard, Dixon Nachu Chega, Makion Kwesi Koga.
Present.
Okay. Introduction to pipelining. Definition: pipelining is an implementation technique where multiple instructors are overlapped in execution. Like an assembly line, different stages of different instructions execute simultaneously, dramatically increasing instruction throughput. So a clear analogy is here. The the analogy. Think of a car wash with four stations. The processes it goes through before the car gets cleaned. So you wash it, you rinse, you wax and dry. So the diagram below indicates the processes involved in pipelining and timing. Pipeline performance and metrics. One, throughput. Instructions per cycle. An ideal end stage pipeline can issue one instruction per clock cycle. Two, speed up. Non-pipeline time. Pipeline time. Ideal speed up for an end stage pipeline equals n dot real speed up is lower due to hazards and overhead. Three, efficiency. So under efficiency, it talks about how well pipeline stages are utilized. 100% means all stages active every cycle, rarely achieved in practice due to stalls and flashes. 4. Latency, single instruction time. Pipelining does not reduce the time for a single instruction. It may increase its slightly due to pipeline register overhead. Clock rate impact. So under clock rate impact, deeper pipelines, higher clock frequencies, into bracket shorter stages equals faster clocks. Pipeline hazards, the real challenge. A pipeline hazard is any condition that prevents the next instruction from executing in its designated clock cycle, causing a stall into bracket pipeline bubble. So these are the processes which causes the pipeline bubble. One, structural hazard. Cause two instructions need the same hardware resource at the same time. A clear example is when a single memory that handles both instruction fetch and data load simultaneously. A recommended solution: resource duplication. Separate one, catch and decatch into bracket close, store pipeline, or reorder instructions. Two, data hazard. An instruction depends on the result of previous instruction still in the pipeline. Example, add R1, R2, R3, sub R4, R1, R5. Sub means R1, but add hasn't written it yet. Solution, forward or bypassing, NOP insertion store instruction reordering by compiler. 3. Control hazard, cause branch instructions. The pipeline doesn't know which instruction comes next until branch resolves. Example, go to label. First wrong instructions must be discarded or flashed. Recommended solution, branch prediction, delayed branching, branch targets buffer, speculative execution. Data hazard, and solutions. 1. Read after write. True dependence. Instruction J reads a register before instruction I write it. 2. Data forwarding. The result is passed directly from the output of one pipeline stage to the input of a later stage, bypassing the register file entirely. Example, arithmetic logic unit results forwarded from EX stage directly to the next instructions via stage input. 3. Right after read, anti-dependency. Instruction J writes a register before instruction I read it. Example is shown below. I'll try to jump some of them since I'm working with more of time. Pipeline stalling. When forwarding can't resolve a hazard, the pipeline is stalled. The dependent instruction waits 1 to 2 cycles. Example is shown below. Write after write. Output dependency. Two instructions write the same register. Order must be preserved. Example is shown below. Compiler or software recording. Sorry, reordering. Smart compilers reorder independent instructions to fill the gap between dependent ones, turning potential stores into productive work. This is called instruction scheduling or code hoisting. Control hazards and branch prediction. The problem branches occur every 5 to 7 instructions on a stage. Sorry, on a 5 stage pipeline. A mispredated branch wastes 2 to 3 cycles. On a deep 20 stage pipeline, like Intel Pentium 4, a mispredation costs 20 plus wasted cycles. These are the processes. 1. Predict not taking. And this is what happens. Always assumes the branch is not taken. Continue fetching sequentially. Simple and free. Works 60% of the time for forward branches, sorry, but fails for loops. Static branch prediction. Compiler or CPU annotates branches. Backward branches predict taking. Forward branches predict not taking based on heuristic heuristics. No runtime data required. Dynamic predictor. Hardware maintains 1 bit history per branch. Predict what happened last time. Problem fails at end of loop when the pattern changes. 2 prediction per loop execution. Saturating counter uses a 2 bit state machine. Strongly taken, weakly not taken, strongly not taken. Must predict, must mispredict twice before changing prediction. Used in RSIC in early advanced pipeline techniques, structural hazards and fix. So these are the techniques under which the pipeline techniques go through. 1. Structural hazards occurs when 2 instructions need the same hardware resource simultaneously. So a solution: fix 1. Duplication. Separate 1 cache and D cache. Harvard architecture. Separate ALU and FPU units. 2. Stalling. Detect conflict. Insert a pipeline bubble. Retry next cycle. Out of order execution. Modern CPUs do not execute instructions in program order. They execute them as soon as their inputs are ready. Array order buffer tracks all in-flight instructions and retires them in order to maintain correctness while executing out of order. The end result: dramatically fewer stores match higher IPs. Superscalar pipelines issuing multiple instructions per cycle. 1. Dual issue pipeline issues 2 instructions per clock cycle from 2 separate execution pipes. Requires the 2 instructions to be independent. IPC is less or greater to 2. 2. Maslow's algorithm. Dynamic instruction scheduling with register renaming eliminates WAR and WAW hazards entirely, used in all modern Intel/AMD processors since Pentium Pro in 1995. Then LIW architecture, which stands for Very Long Instruction Word. Compiler packs multiple operations into one wide instruction. Hardware is simple. Complexity shifts to the compiler. Used in Intel Titanium DSPs. Speculative execution. CPU executes instructions before knowing if they are needed. Example, cast a branch. Results are discarded if wrong path taken. Powers massive performances, but see sector or meltdown. Parallel processing architectures. Lens taxonomy, 1996. The gold standard classification of parallel architectures. 1. Single instruction, single data. In short, SISD. The classic von Neumann machine. One processor, one instruction stream, one data stream. Standard sequential execution. A clear example is where simple 8-bit microcontrollers, early Intel 8066. 2. Single instruction, multiple data, in short SIMD. One instruction operates one multiple data items simultaneously, ideal for vector/array processing, graphics, ML, example, Intel AVX 512 bit equals 16 floats at once. GPU shader cores ARM Neon. Multiple instruction single data, in short MISD. Multiple processors execute different instructions on the same example. Fault tolerance fault tolerance system. Space shuttle flight computers pipeline states are sometimes classified as MSI. Multiple instruction, multiple data, in short MIMD. Multiple autonomous processors each execute their own instructions data, on their own data, sorry. Most powerful and safer category. Example, multi-core CPUs, Intel R9, AMD Ryzen 9, server clusters, distributed computing. Parallel system design. 1. Shared memory. All processors share a single physical memory space via a system bus or called bus switch. Distributed memory. Each node has its own private memory. Processors communicate by explicitly sending or receiving messages over a network. GPU parallel architecture. GPU contains thousands of simple cores. Example, NVIDIA H100, 18, 432 CUDA cores, optimized for throughput, not latency. Uniform memory access, in short UMA. Every CPU takes the same time to access any memory location. Scales to thousands of nodes under distributed memory, scales to thousands of nodes, powers the world's fastest supercomputers. Example for 8.7 core. And GPU parallel architecture organizes threads into warps. Example 32 threads. All threads in a warp execute the same instruction in lockstep. Shared memory 3. Easy to program. Threads communicate via shared variables. Cache coherence is the main challenge. And distributed memory. Programming model. Message passing interface (MPI). Explicit send or receive calls between processors. And that GPU parallel architecture. Memory hierarchy. Registers shared memory, non-uniform memory access, short NUMI, NUMA. Each CPU has local memory, fast and liquid, ETAMD, APYC service, and distributed memory, interconnect, InfiniBand, 200 GPS, MVP link, and GPU architecture programming, CUDA, example, NVIDIA, OpenClaw, ROCm. AI training relies almost entirely on GPU parallelism. Summary, real-world application and pipelining overlaps instruction stages to increase throughput, not single instruction. Hazards, structural data. Example, RAW, WAR, WAW. Control hazards or reduce IPC low ideas. Forwarding, resolve the most hazards in hardware with zero or minimal store cycles. Branch prediction. Modern predictors achieve greater greater 99% accuracy. This mis predictions still cost 15 to 20 cycles. SIMD slash MIM dominates graphics and AI workloads. MID underpins all multi-core computing. So in real world application, AI and deep learning, video processing, scientific computing, database engines. And this brings me to the end of the presentation. Thank you. Hello, please, I'm done.
All right. Please, do you have any question for them?
Yes, sir. Please, I have a question. Hello, sir.
Can hear you.
Okay. Thank you for the presentation. But I wanted to know the type of pipelining. Since you didn't point on that with a superscalar pipelining, and then with pipelining, you want you to give more explanation on the efficiency, and then with speed when it comes to pipelining, and then touch a bit on that is if time will permit us, and then you touch a bit on the hazard again. I didn't actually get the explanation well. Thank you.
Okay. David.
No.
Yeah. How many groups are left more?
So it's left with group 1, group 8, and then group 7.
3 groups more.
Yes.
Okay. All right. We'll continue, God willing, next week. Thank you.
Okay, sure.
Please, next week is Easter break. Oh.
Yes. Sure. I will inform you.